Okay, hello guys, and welcome back to another episode or another version of the I Explain CCC Junior Solution. So the year is 2025. Let's just jump right in. Um, Problem J1. So basically, this problem is asking for whether or not we're going to make it onto the roller coaster if the roller coaster has this many carts and this number of people per cart. So obviously, if we multiply these two numbers together, the C and the P, we're gonna get the number of people in like the entire ride. So obviously, if we are ahead of line of like if our place in line is less than or equal to this number, we're gonna make it. So we can see 3 times 2 is 6, 14 is greater than 6, so the answer is no. 3 times 4 is 12, and 12 is less than or equal to 12. So the answer is yes. So it's very simple. We have NC. Let's just get all that, and then let's say int total equals C times P. And then if n is less than or equal to total, then we print yes. Otherwise, we print no. So let's just submit this. There we have it. That's J1. Moving on to J2, we have donut shop. So for this one, we're going to have to handle some events. So first of all, we know that there are D donuts at the beginning of the day. And then we have E events. In each of these events, we either get plus donuts or minus donuts. So this one is basically a simple for loop. Not too much to say about this. We can get, first of all, D, the number of donuts, and then E, the number of events. So E and E. And now for each event, so let's do a for loop with the number of events. We're going to get a character, which is going to be the plus sign or the minus sign. So here we go. And then we're going to get the integer. So this way we're getting the character first. So we see the plus sign or the minus sign, and then we get the number. So then we can say if C is equal to plus, then we say D plus equals X. And then otherwise we subtract. Because, you know, plus sign means addition. That means that we have to add this number to our existing number. And then finally, we can just print out the number of donuts left at the end of the day. And submit this. There we have it. Great. J3. So here is where it starts getting a bit tricky. So most people can solve J1 and J2, no problem at all. But J3 is where it starts getting difficult. So for this one, we're basically told to implement a procedure. And this procedure is we keep all the uppercase letters in their original order, remove all the lowercase ones, and then combine all the numbers. So what does it mean by combine all the numbers? Let's take a look at an example case here. So we have 393, 5, -9, and -8. Oh, and we also have 6. Whoops. So basically what it wants us to do, if you read the problem description, is it wants us to take this number, so 393, and since there's no minus sign, that means it's positive. So 393, and then plus 5, because again, there's no minus sign, plus 6, -9, and -8. And that's going to give us 387. And the number will always come at the end. Okay, great. So let's do this. J3. Okay, so this is just our input. And now we've gotten the string. So again, let's do it in order. So first, when we say remove all lowercase letters, we can literally just simplify that to keep all the uppercase letters, right? So let's make a string called the ants for answer. And then we're going to go through every character in S. And we're going to say if the character is uppercase, so if it's between uppercase A and between uppercase Z, then we add it to answer. So currently what this does is it gets the all the uppercase letters only, but we're still not taking into account the numbers, and we still need to do that. So for this, we're going to need a bit of a more complicated loop. Let's say int current equals 0. So this is going to store the current number that we have. What we're going to do is we're going to loop through the string again. And then what we can do is as soon as we encounter a digit, we keep scanning to the right until we don't see a digit anymore. So for example, here we see 3. Okay, great. We're going to keep going. 39. That's still a number. Okay, 393. That's still a number. 393H. This H is not a digit, so that's when we stop. So we can do this by saying if is digit si. So if it's a digit, then we're going to say j equals I. So we're going to make a new pointer. So we have a new index, sort of. And this index is going to keep scanning to the right until we reach a non-integer. So we're going to do while j is less than s dot size. So that way we don't go out of bounds of the string. And is digit sj, j plus plus. And actually there's a better way to do this right here. So we can say our number is 0. And then in this loop, when we're looping right, we can do number equals number times 10 plus, and then sj minus 0. So what this does is it basically gets this number. And how does it do that? So when we have 3, first of all, so our number starts at 0. Let's simulate this. So simulate this. We start 393, and our number is 0. When we first encounter the 3, we hit this is digit if statement, and we set j equals I. So this j is still pointing to the 3. We have number set to 0, and then we're going to do while j is less than s dot size, and it's a digit, we multiply by 10 and add the digit. Okay, so this is still a digit. So what we're going to do is we're going to take number times 10. 0 times 10 is still 0. And then plus 3. So now we get 3. Great. Now we're going to keep going. 9. Is 9 the number? Yeah, it is. So we're going to multiply num by 10. And then add 9. That gives us 39. Great. Now we keep going. 3. That's still a number. So we're going to multiply this by 10. We're going to add 3. And that gives us 393. So basically what we're doing here is by multiplying by 10, we are sort of like shifting this number up in the number system. Because again, we use base 10 or decimal for counting. And that means every time we multiply by 10, we add a 0 to the end. So that's how we're parsing these numbers. So now we have the number. And then here's a bit of a more tricky part. So we need to check, first of all, if there's a negative sign. But the problem is we only enter this if statement when we're at this number. So how do we do that? Well, it's actually very simple. So we can just say if I is greater than 0 and si minus 1 is equal to a negative sign, then number times equals negative 1. What does this mean? So first of all, this should make sense, right? If the character at the index before a number was a negative sign, then we need to negate the number. But why do we have to check if I is greater than 0? Again, we need to make sure we're not going out of bounds. So if the first digit is a number, and we try to check before that, well, we can't go before the first character. So that's going to cause an error. That's why we need to check if I is greater than 0. And if it is, then we multiply by negative 1. Like if we find the negative sign, we multiply by negative 1. And now we can just say current plus equals number. So we add number to current. We set I equals j minus 1. That way we don't double count. Because now our j has gone on to the next character. That's an h in this string. So if we keep going, if we ignore where j ended up and we keep going with I is going to look at 9 now. And it's going to count 93. And then it's going to count 3. And that's not good because we want to only count the number once. So finally, we can now just print out the answer and current. So that way we get all the uppercase letters and then we print out the number. So we can compile this. On this test, and it gives us AXCV -5, UHQS 387, and this thing 1166. Looks right to me, so let's submit this. Great, accepted. Moving on, now we get J4. And J4, I'm not gonna lie, it was actually kind of tricky. I spent quite a long time on J4, mostly because of stupid errors, but also because I didn't read it carefully. So hopefully you guys learn from me and make sure to read it carefully. So let's go. So we have this weather report. We have n data points, and each point we either get its raining, which is P precipitation, or it's sunny, which is S. And we're saying there's exactly one day where it's incorrect, but we don't know what day it is. So we want to find the maximum possible consecutive days with sunshine. This sounds easy. In theory, it's easy, but the implementation gets a bit difficult. So first of all, how are we going to approach this? Let's take the example input. And let's take a closer look. So we want the maximal number of sunny days in a row. So let's look at each P and just try it. This becomes an S. That gives us two S's in a row, two S's in a row, and one S in a row. So the maximum is 2 in this case. So we change this, the maximum becomes 2. What if we change this one? This one becomes an S. Now we have, oh, we have 4 in a row. Pretty good. What if we change this one? Well, that's 3 in a row. And if we change this one, obviously it's 2 in a row. So our answer is 4. Great. But the problem is this algorithm is slow, the one I just simulated, because I had to try changing every single P into an S and then checking it over again, which ultimately runs in O of n squared time, which means it's going to pass all of these cases, the 2 mark and the 4 mark one, but it's not going to pass the 9 mark one. So we need a better approach. And here we have an algorithm that actually allows us to do this in a slightly better way. So the one that I first came up with was we store all the consecutive S's. So we say here we have 1 consecutive S, here we have 2 consecutive S's, and here we have 1 consecutive S. And what we can do is we can go through each of these segments almost, and then in the break between 2 segments, we check if there's only one element. Because if there's only one thing separating these two, if we change this one thing to an S, we can combine these two into 4. And it's the same logic for these two, except it's not one thing. So even if we change this one to an S, this one's only going to become a 3. So let's implement this approach and see if it works. So let's first of all define PII pair int, and we have int n vector PII a. Also Boolean array for the entire thing. Let's get n, and then for each thing, let's just store sunny as true and then raining as false. So we say if c equals s, then we say ri equals true. And otherwise it's going to be false, but that's already implicitly defined because every value inside this array is going to start out at false. Okay, so now what? Now what we want to do is separate it into these consecutive runs of s's. So we can use a very similar algorithm to what we just did here, where we keep looping forward while this condition is satisfied. But in this case, we keep looping forward as long as we keep seeing an s. So we can do for, right, same thing, and if ri. So if we have an s currently, set j equals to I, and then while j is less than n and j is sunny, we increment j. And then finally, we can push back the segment here. So essentially what I'm doing here is I'm storing the endpoints. So this would be denoted as pair. So let's say this is index 0, this is index 1. This would be a pair 1, 1. And this would be a pair 2, 3, 4. This would be a pair 3, 4. And this would be a pair 7, 7. And then, of course, I plus j minus 1 right here. So we have these pairs now. How do we implement the algorithm that I just described? We have 1, 1. We have 3, 4. We have 7, 7. So if we want to check if two things are next to each other, we just have to check if the endpoint of this and the starting point of this are 2 apart. So if, let's say this is S and this is E. So if S minus E equals 2, that means they are consecutive. So first, let's make a variable called answer, and then we do the exact thing that I just said. I just segment, oh wait, it's called a dot size, and let's say auto s e equals ai. So we have the starting point and the end point. We can say the length is e minus s plus 1, because if we look at this 1, 1, we take 1 minus 1 is 0, add 1, that gives us this length is 1. This length is 2, and this length is 1. So we have the length now. Let's assert something. So let's say in almost all cases, when we have a bunch of s's and then a p, what we can do is we can override this p into an s and then cause the length to increase by 1. So this used to be 2, and once we overrode this p with an s, it became 3. So what we can do is we can say ants, let's say current is equal to length plus 1. So that's the maximum size. And we see if we can possibly expand the next one by changing the next p into an s. So we can say if I is less than a dot size minus 1. So again, we don't want to go out of bounds. And we say and a I plus 1 dot first. So the starting point is equal to n plus 2. So if they're consecutive, then we can just add the length of the second one to our current thing. So plus equals ai plus 1 dot second minus that plus 1. Just like that. So now we have this. Let's see if it works. So again, ant is equal to maximum ants curve. We want the maximum possible length. So let's print ants and see if this works. So for example, input, and it gives us 4. Great. And let's submit it then. Huh. Okay, so we pass almost all of the cases except for the first few. What's going on? Well, the main key insight is that we say that the data is incorrect for exactly 1 day. Now, what happens in the case where our 1 day, we only have one measurement, so we have n equals 1, and that one measurement is s? Well, we know it's incorrect for 1 day, and there's only 1 day for it to be incorrect. So this s has to be a p. Similarly, if we have n equals 2 and we have two s's, one of these s's is incorrect. So it has to be either sp or ps. So our issue is that in the case where there's only s's in the string, sometimes the answer is going to be less than the number of s's. But this is pretty easy to check. We can say if, so count array plus n, 1 is equal to 0, or is equal to n. So if we have n s's, so all of them are s's, then we need to print n minus 1 and return 0. So now if we compile it, we'll see if we put 1s, we get 0. Great. Let's see if this is fixed then. Wow. Okay, well, it passed one more case. So what could be going wrong? Is there a different case that we forgot to account for? In fact, there is actually. Because now we also have the case where there's only p's in the string. So if we have all p's, or n equals 1 and there's one p, this has to be an s. Are we counting for that? No, we're not. So we also need one more case to check if there's only p's in the string. But that's pretty easy to account for. We can say else if count array plus n 1 is equal to 0. So if there's no s's, then we have to print 1. And now let's see if it works. And there we go. We get accepted on all the cases, and that's just the J4 solution. Finally, we have J5 connecting territories. So this J5 was a bit of a more tricky problem. Notice the time limit is 5 seconds, so that tells us we might be doing something a bit slow. And although it might look tempting to use math for this, because it looks like it's math, right? It's just 3 integers. I think the much easier way is to use dynamic programming, or DP. So let's just write the boilerplate code. So currently, so we have RCN. Now let's get those. Okay, so now how are we going to do this? So we have our upper territory and we have our lower territory, and our goal is to go from the upper to the lower using the minimum possible cost. First of all, though, since we don't actually get the grid, we're going to need something to determine what number is in a square. How do we do that? So we can notice we have a pattern, right? We go from 1 to m, and then we start over again. So that means if we can determine, so let me take a screenshot of this. If we can determine how many squares are before us, so let's say we're on this square right now, if we can count the number of squares in this region, then we can easily calculate the number that goes in this box. So in this case, let's simulate this. How many numbers are in this region? So in the first row, we have 8, and in the second row, we have 3. So that means that we have 11 numbers before us. And we know m is equal to 5, so it has to repeat every 5 numbers. Okay, this is modular arithmetic, right? So we have 11 mod 5, or %5, is equal to 1. And since our number starts at 1 as opposed to 0, we need to add 1. So basically, what we do, let's say f of x and y, and we also have the variables r and c for the number of rows. So r goes this way and c goes this way. So we say the number in the box is gonna be it's gonna be x times c plus y. And let's say this one is x equals 0, x equals 1, x equals 2. So I'm using the standard array numbering system, 2D array numbering system. So this starts at 0, 1, 2, 3, 4, 5, 6, 7. And then, so we have this is a number, and now we have to take that mod 5 plus 1. So does this work? Let's see f of 0, 0. So it gives us 0 times c, we don't care, that's still 0, plus 0. So we have 0 mod 5 plus 1. 0 mod 5 is still 0, so this gives us 1. Great, now let's try f of 1, 0. So we're looking at this square right here is equal to, so x times c, c we know is 8. So we have 8 plus y is 0. Mod 5 is equal to 3 plus 1. That gives us 4. And that's correct. So this is the first part of solving the problem. We need to be able to determine the number in a grid point in a fast way. Instead of creating an entire grid, which is slow, we can do this. So let's write a function for that real quick. Let's just say int get num. We have ij as the array index. So first I is the row, j is the column. And we just implement this formula. So we have return x time or I times c plus j mod 5 plus 1. And we need parentheses around these. And there we go. So that's the first part of the problem finished, semicolon. Now how do we find the shortest distance from the top to the bottom? Well, if you're familiar with recursion, that probably is the first thing that comes to mind. And you'd be right. You do need recursion for this. So how does recursion work? Well, we know we can't go back up, so we have to be going down at all times. That means we go from here and then to here. So from each box, we have 3 choices to go down. And then again, 3 choices for this, 3 choices for this, and 3 choices for this. So we can use recursion to simulate this process by going through every single grid in the first row, or yeah, every single square in the first row, and then checking the minimum cost to reach the bottom through any combination of path. So we might go here, we might go here, we might go here, we might go here, we might go here for 1. For 5, we're gonna go some kind of combination of the paths along here. I can't really draw out every path because there's a ton, but recursion will be able to handle that. So how would we write our recursive function? So we can say, let's write some pseudocode real quick. So let's say our function returns an integer. That's really big. Whoops. Integer. And this integer is going to correspond to the cost to reach a certain square. So let's say int find path, and then we have the current square, its dimensions. So we have the I and the j, or the x and y coordinate. Okay. So what do we put inside? First of all, let's say if we are on the bottom part, so if the I is equal to row minus 1, because it's 0 indexed, then return get num ij. So this way, if we are all the way at the bottom, we just get the number. Otherwise, what we're going to do is we're going to say, if my spacebar is going to work, I guess not. Okay, I'll just do this. Okay. So otherwise, what we're going to do is we're going to take the 3 options. So we have go down and to the left, go down only, and go to the down and to the right. So we want the minimum cost path, so we return the minimum among the 3. So we can say return min. So the minimum of, where's my cursor? Here it is. So the minimum of find path I plus 1, j minus 1. Find path I plus 1, j. And find path I plus 1, j plus 1. So what we're doing is when we reach a bottom row, we return the number directly. Oh, actually, I need to say min this and then plus get num. Forgot. Get num ij. So essentially what we're doing here is we're starting out with, let's say, this 4 right here. We're going to recursively call each of these squares to make them do the recursive function. Each of these squares is going to recursively call these squares, and so on and so forth until we reach the bottom. And when we reach the bottom, each square just returns its own value. So let's say our path that we just traced was 4, 3, 2, 5, 3. So once this returns, and let's say 5 sees that 3 is the smallest one. Just an example, although it's not true, it's just an example. 5 sees that 3 is the smallest one, and then 5 is gonna have this thing, this big min is equal to 3, and it's gonna add itself. So it's gonna add its own get num, which makes this 8. And then it returns this 8. Up to the 2, this 2 sees, oh, this 8 is a minimum, and then the 2 um, adds itself, so now we have 10. It goes up to the 3, adds itself 13, adds this 17. Just as an example. So this is roughly how our recursive function is going to work. Let's write this out real quick and see if it works. So again, we have int find path, int I, int j. We say if I is equal to r minus 1, return get num I, j. Otherwise, we return the minimum of find path I plus 1, and there we go. I plus 1j, I plus 1j minus 1, and I plus 1j plus 1. There's an issue though, and that is, let's say we start out at the 1. If we start out at the 1, and we try to say find path I plus 1j minus 1, so if we try to go left, we go off the screen, or in other words, we go out of bounds, and that's going to cause an error. So we want a way to handle this out of bounds case. And we say if j is less than 0 or j is greater than or equal to c. So if we're either out here or all the way out of the screen to the left, we need to do something so that this case doesn't get considered. And since we're finding the minimum among all these, we can simply return a huge value. So let's say return like 10 to the 9, a huge value that will not get considered at all. So that way, it basically just gets ignored. Great, so now we've returned 1e9, and this should work now. So we say int ans equals 1e9. Again, this way we're setting an ans to a huge value at first, so we can find the minimum among all these. So we can loop through each column, and we're going to do ans equals min ans find path 0i. So for each of these first row things, first row squares, we're going to look through each of them and run the recursive function, and then we're going to see the minimum path that it gets. And then we take the minimum among all of these. So then now we just print the answer, and that's it. Let's test it on the sample case first of all. It gives us 1. That's not right. What's going on? Is this right? I times c plus j mod 5 plus 1. Yeah, that's right. So we should be taking this 3, 2, 1 path, but we're oh, I forgot to add get num. Okay. That's a pretty stupid mistake. Now this should work. We get 3 now. Let's see what's going on. So if this coordinate is out of bounds, we have to return a nonsensical, a huge value, obviously. And if we reach the end, we need to return the number, because there's no point in continuing. Otherwise, return the minimum among each of these find path function calls. Okay, so I'm using 5 instead of n. That's really great. That's the issue. Let's try it again. 3, 5, 7. And now we get 6. Let's go. Great. Now let's submit this and see how it does. Okay, we got mostly accepted. But our submission is hanging now. What's going on? Time limit exceeded. On which case? This one, where there are 100 rows and 100 columns. The reason why this is happening is because our code is actually exponentially slow. So you can pretty obviously see that on each layer, we're exploring 3 new states. So for each square, we explore 3 new things. And we start by exploring however many columns there are. So we can say this code runs in the order of 3 to the power of r, because there are r, like it goes r deep. And this is not fast at all. It might work for r that's less than 10, right? Because if there are only 10 rows, 3 to the power of 10 is like a couple million, which is reasonable. But 3 to the power of 100? No, that's a couple, that has to be more than like a trillion. Yeah, that's definitely more than a trillion. Not even close. Yeah, okay. So clearly our approach is a bit too slow. How can we speed it up? First of all, you might have noticed that aren't we doing a bunch of redundant calculations? Because we've seen, so as this, let's take this 4 as an example, and let's say we've already calculated each of these squares, and now we're calculating 2. If 2 goes here, and then 2 goes here, we've already calculated this number. So we shouldn't need to calculate it again, because that's just dumb when we've already calculated it and the value's not going to change. So this technique is called dynamic programming, or DP, and in DP, we store the previously calculated value so that we can use it for new calculations. So let's say, let's make a DP table. So this is how we store our results. DP, let's say just 1,000 and 1,000. And then when we return things, we return dpij equals getNum, and return dpij equals this. So this way we cache the results, and also we say if dpij, then return dpij. So if we already have a value here, then we just return it, because we've already calculated it, so we don't need to keep doing the recursion. And just to verify as a sanity check that we haven't done anything terribly wrong, let's run this, and we still get 6. That's good. And let's submit it. Okay, so now we've gotten this case where there are 100 rows, but what about this one where there are 20,000? You might be tempted to just go, oh, let's just 20,000 and 20,000. But this won't work. If we pull up a calculator real quick, how much is 20,000 squared? 400 million. Can we store 400 million values? Well, let's just assume one value is 1 byte. That's 400 megabytes. How much memory do we get? 256. There's no way we can store that entirely. So we need a better way of doing this. And here is where we have to get rid of recursion, unfortunately, because recursion is just going to be too slow, and it's not going to be able to use the method that we are going to use now. So let's rethink this a bit. Remove all this writing. Let me just make an entirely new canvas. Let's think about this again. We've already seen that we have to go downwards. We can't go back up. Can we take advantage of this? What if we start by processing each of the rows? What if we start by processing this row, this row, this row? And then in each row, we store the minimum cost to reach that square. So let's say, let's write in red real quick. Minimum cost to reach the square is 1, 2, 3, 4, 5, 1, 2, 3. Obviously, it's like this because if we want to stay here, we just need to spend 1. And then for this one, the minimum cost to reach here from the top is going to be 1 plus 4. It's not going to be 2 plus 4 because that's 6. So this one is going to be 1 plus 5. This one's going to be 2 plus 1. This one's going to be 3 plus 2. This one's going to be 1 plus 3. This one's going to be 1 plus 4, 1 plus 5, and now 2 plus 1. And we keep repeating this process of selecting the minimum among the 3 upper level neighbors. So in case you haven't caught on already, what I'm doing is I'm looking at this, looking at the 3 ones that can go to it, picking the minimum, and then adding it to this value. So we can keep doing this and filling up each of these values until we reach the bottom. And then at that point, the answer is going to be the minimum value in the bottom row. Okay, great. So how can we do this then? Well, you might think we still need a 2D array, right? If we want to store all these values. And like you just said, that 2D array is going to be way too large because it's going to be over 400 megabytes. So how do we do this then? The key is that we don't actually need to keep track of the entire thing. When we finish with a row, we're just done with it. We don't need it anymore. We can just do this next row using the previous row that we just got. So if we calculate this row, it's going to be 7, 6, it's going to be 7, 8, whatever, it doesn't really matter. The key idea is that we don't care about this result anymore because we've already used it to create this row. That means we only need to store 2 rows worth of data, which is much smaller because we know a column has almost 20,000 things. Multiply by 2, we get 40,000. So we only need to store 40,000 elements, which is 40 kilobytes basically, which is tiny. Okay, great. So let's try it then. How do we implement this? So let's create a vector or an array for the current one and an array for the previous one. Let's call vector int, call it current and then previous. So for the first row, we're going to set, so for each row, we're going to set the current one to the elements of the row and then plus the minimum of the 3 neighbors. So for I equals 0, or in j equals 0, j is less than c, j plus plus, we're going to say current j is equal to get num ij plus minimum of 3 previous ones. And once we finish this row, so let's say we finish this second row, and now we're moving on to the third row, we set the second row to the previous one, and then the third row we start adding back on. So we say previous is equal to current. And also there's still another issue here. We might be going out of bounds here. So we can just do a special check. So this out first of all. So if j is greater than 0, and current j is equal to get num ij plus min. Actually, okay, there's a better way that I like to do this. Some people might criticize me for this, but what I like to do is I like to make a new function to safely get values. So get prev int I and then vector int reference prev. So if our index is out of bounds for the previous DP array, then we return, again, a huge value that will make no sense. Otherwise, we return the value that we already got. And now what we can do is we can just do minimum get prev, just like that. And now our algorithm should work. Let's try it. Again, just sanity check, 3, 5, 7. Ooh, that's not good. Right, the problem is we haven't actually calculated the answer. So for each iteration, or at the end, we can just say ants is equal to the minimum element of the current iteration. 3, 5, 7, and that gives us 6. Now let's submit this and see how it goes. It's thinking. Okay, accepted on 1, 2, and there we go. So that's the entire junior contest this year. It wasn't too bad in my opinion. J4 is a bit tricky if you didn't read it carefully, but aside from that, it was a pretty okay junior contest. So let me know your thoughts in the comments. What'd you get? How'd you do? What'd you think of the problems? Did you enjoy them? And also let me know if you want to see a senior video, because I did the senior contest this year and I was almost able to qualify for CCO. I don't think I'll be able to, even though the cutoffs are not out yet, but we will see. So thanks for watching.